In our journey in regression analysis, we have so far focused on simple linear regression. Simple means that there is one x and one y. We're using one variable as the independent variable to predict another variable called the dependent variable. We have checked, for example, the relationship between advertising and sales. These are two variables that have been combined in some way through a linear regression equation, y on x. What if there are other variables? In addition to advertising, let's suppose that I've got other variables. And as you can imagine, that is what machine learning algorithms do. They have many inputs and get an output. If you want to think of even very sophisticated algorithms like sentiment analysis on text, there are many text features which will go in to predict one number. Similarly, facial recognition, many features of an image to go into predicting one number. So therefore, we need a mechanism by which we can take many inputs and use them together or collectively predict an output. And that is multiple linear regression. Multiple stands for multiple x's. Linearity will still hold, as we'll see. We'll still get a linear equation. So now let's suppose that we have advertising expenditure as one input and we have a second input, let's say discount percentage. We expect that discount percentage will also impact sales. Greater the discount percentage, we can expect greater sales. So which promotion mechanism should we use? Advertising or discounts? And how do they trade off against each other? And how do I get an effect of each of them in some way separately? That's the kind of question that we'll be going after. Once again, a mathematical model linking this time multiple inputs to a single output. The output remains one variable. That we're not going to change. Two or more explanatory variables and one response variable. This is an extension of simple linear regression, and the same ideas will work to get us an answer. So multiple linear regression now has an equation of the form y is equal to b0 plus b1x1 plus b2x2. There are two x's. If there are more than two x's, you know what's going to happen. I can write this as b3x3 and so on and so forth. The ideas will be the same. So let's stick to simply explaining it in terms of two x's. This is now not a line, but it can still be interpreted in the same way as we saw our line to be. What is x1 here? Advertising expenditure. x2 is discount percentage. Y is the sales. We've added the x2 variable, and with it, we have carried a new coefficient, b2. These are the coefficients of multiple linear regression. There are as many slopes as there are input variables or explanatory variables, and there is still one intercept. Is it still a line? Well, close to a line. It is a line in a higher dimension. In 2 dimensions, we can draw this line. In 3 dimensions, that is 2 x's and 1 y, we still have to draw the same way, but in 3 dimensions, the line is going to look a little different. In fact, we don't call it a line anymore, we call it a plane. So it is a linear function. Y is a linear function of x1 and x2, and when we plot it, we get a plane. So if you're in a room seeing this video, you can think of the floor as being your x1 and x2, and think of the height of the room as representing the y, and think of this equation and plot all the points on that equation, and what you'll get is like a sloped plane. In higher dimensions, incidentally, above 3, these are called hyperplanes, and they can be as high as possible so long as they retain this linear equation form. We won't need to worry about the geometry at all, because as you'll see, the algorithms will be remarkably similar, and it honestly won't care as to whether we have 2 x's or 3 x's or 4 x's. So when we get to this kind of an equation, we can again get coefficients. You can in fact guess where these coefficients are going to come from. They're going to come from some kind of least squares criteria. like in simple linear regression. But for now, let's focus on the equation itself. So let's say here is an equation. 1.01 plus 2.45 advertising expenditure plus 7.88 into discount percentage. So I've added this last term. By the way, it is not generally the case that when I add a term to an existing linear equation, the equation does not change. There are special situations where adding a term does not disturb the original equation, but in most cases, the original equation will also change. But we leave that aside for now. We have an equation. What do these numbers now mean? They mean something slightly different from what they meant before. Let's look at the first number. We say that sales will increase by 2.45 units if advertising goes up by 1. So if advertising goes up by 1 unit, a unit increase in advertising, sales will increase by 2.45 units as before. Same interpretation. There's a catch, because in my data set, there is an additional variable, my discount percentage. So for this interpretation to hold, discount percentage is not going to change. It has to be held constant. So what this means is that if I have a unit increase in advertising expenditure and my discount percentage stays the same, then my sales is expected to go up by 2.45. And the same kind of principle could work for the other variable as well, which is 7.88. So if there's a unit increase in my discount percentage, then my sales will go up by 7.88, provided there is no change in advertising expenditure. So the regression coefficients reflect the effect of that variable, the variable that coefficient is hitting, provided the other variables are not changed. This interpretation might become problematic and may not make sense in many business situations. So therefore, again, we check whether the assumptions of linear regression hold true or not for this to be meaningful. But it is still a powerful summary statement to have of a predictive model. To say what is the effect of each variable singly on the output, taken one at a time on the output, paying the price of forcing the other variable to be fixed. So that's the interpretation of the slope. The intercept remains problematic or interesting in exactly the same way. Now, for multiple linear regression equations with more than 2 explanatory variables, do I have to think of something different in order to get my equations? What did we use in our previous thinking that was required only 1 axis? And if I can extend it to 2 axes, can I extend it to 3 axes, 4 axes? There shouldn't be a problem, right? The same principle should work. So if I've now got 3 axes, let's say I've added price to the mix. For those of you who work in marketing, you know the 4 P's of marketing. We've been talking about promotion, which is my advertising and my discount, but another P is price. So I might say, what about price? And price can just be added again to the equation, and exactly the same kind of equation and exactly the same kind of interpretability can be added to it. In this particular case, one might expect, should one build a model of this kind, that beta 3 or B3 here will be negative. One would expect that B1 is positive, B2 is positive, and B3 is negative. Why is that? Because all else kept the same, advertising increase should increase sales. All else kept the same, discount percentage increase should increase sales. All else held the same, price increase should decrease sales. So in multiple linear regression, figuring out the sign of the coefficient gives very interesting insight as to the way individual variables affect the outcome. Whether these variables are actually there or are zero is something the statisticians worry about. is this coefficient actually there, or can I not lose predictive power by just dropping it? We're not going to go that far, but these coefficients are also useful in that sense, to check for whether that x should be there or not by comparing the slope to 0.